Look around you. The house you're in, the road you drive on, the bridge you cross to get to work, none of it would exist without civil engineering. It's the backbone of our modern world, the silent, sturdy force that keeps everything standing. But what holds up the engineering? The materials. Getting the materials right is everything. If you use the wrong stuff or you use the right stuff the wrong way, you're not just building a project, you're building a future problem. A big, expensive, and dangerous problem. We walk into towering office buildings in Accra, like the Villaggio Vista, or drive over massive structures like the Adomi Bridge, and we don't think twice. Why? Because we trust that the engineers chose the right steel, the right concrete, the right everything. This trust is built on a science of selection and testing. It's not a guessing game. First, we can look at their origin. Are they natural, like the stone and timber we pull right from the earth, or are they manufactured like the steel and plastics we create in factories? So you've got a project. How do you pick your players? Material selection is a careful balancing act. The first thing everyone looks at is cost, but choosing the cheapest option is almost always the most expensive mistake you can make. What you save today, you will pay for tenfold in repairs and replacements down the road. A better quality material might cost more upfront, but if it lasts twice as long and needs fewer repairs, you've saved a fortune. Then, you have the rulebook. Every country has standards, and in Ghana, you have the Ghana Standards Authority. To make sure materials meet these standards, we test them. We push them, pull them, crush them, and soak them to see what they're made of. We test for properties like plasticity, how much it can be bent without breaking, and hardness, its resistance to scratches and dents. We measure density to understand its weight and specific gravity to compare its weight to water. We check its moisture content because too much water can ruin materials like concrete and wood. We even analyze its chemical properties to make sure there are no impurities that could cause it to fail years later. They tell us if it will be tough enough to handle an impact or ductile enough to bend instead of snapping under pressure. Let's talk about the king and queen of construction, concrete and steel. First, cement. A lot of people think cement and concrete are the same thing. They're not. It's a fine powder made by heating limestone and clay to incredibly high temperatures in a kiln, creating something called clinker. This clinker is then ground up with a little gypsum, and voila, you have cement. When you mix this powder with water, a chemical reaction called hydration starts. This reaction is what creates the strong, stone-like paste that binds everything. This paste is then mixed with aggregates, sand and gravel, to create concrete. The magic is in the mix. The recipe, or mix design, is critical. You need the right ratio of cement, water, sand, and gravel. The water-to-cement ratio is especially important. Too much water creates a weak, porous concrete that will crack and crumble. Steel is the opposite. It's fantastic in tension. By embedding steel reinforcement bars, or rebar, inside the concrete, you get the best of both worlds. The concrete handles the compressive forces, and the steel handles the tensile forces, but you have to do it right. Common failures happen all the time. If the rebar is placed too close to the surface, moisture can get in, causing the steel to rust. Rusting steel expands, cracking the concrete from the inside out. This is called spalling. You have to protect your steel, get your mix right, and give that concrete the time and moisture it needs to become rock solid. While concrete and steel get most of the glory, there are other crucial materials on the job site. Take aggregates, the sand, gravel, and crushed stone that make up the bulk of concrete and asphalt. We perform tests like sieve analysis to ensure we have a good mix of different particle sizes called grading. Then we have bituminous materials, the black sticky stuff we use to build our roads. Just like with concrete, the mix design is crucial. You have to heat the bitumen and aggregate to the right temperature. A common failure you see on roads everywhere is potholes, often caused by water getting under the asphalt. Timber, or wood, is one of our oldest building materials, and it's still widely used for framing, roofing, and finishing. However, its biggest enemies are moisture and insects. In a place like Ghana, termites can destroy untreated wood in no time. That's why timber must be properly treated with preservatives to protect it from rot and pests. Finally, you have a whole range of other materials like plastics, which are now essential for things like water pipes and insulation. In the end, it all comes back to a simple principle. Understand your materials, know their strengths, respect their weaknesses, and follow the best practices for installing them. If you make the right choices and refuse to cut corners, you're not just building a structure, you're building something that will last. You're making it right. When you drive down a smooth road or walk across a city street, you're likely traveling on asphalt, a material that's everywhere but rarely noticed. In civil engineering, asphalt and bituminous materials are the backbone of road construction, prized for their flexibility, weather resistance, and ability to handle heavy loads. Let's break it down. Bitumen is a black, sticky substance derived from crude oil. When mixed with aggregates like sand and gravel, it forms asphalt concrete. There are several types of asphalt mixes, including hot mix asphalt, which is produced at high temperatures for major highways, and cold mix, often used for patching and minor repairs. The properties that matter most: stability, flexibility, and durability. Engineers test asphalt in the lab to measure things like penetration, how easily bitumen can be deformed, and viscosity, which tells us how it flows at different temperatures. Another common test is the Marshall Stability Test. It checks how much load an asphalt sample can withstand before it fails. But even the best mix can run into trouble. Common failure modes in asphalt pavements include rutting, which is permanent deformation under heavy traffic, and fatigue cracking, which happens when the pavement flexes too much over time. Then there's the infamous pothole, often caused by water seeping below the surface, weakening the layers until the asphalt collapses. Despite these challenges, asphalt remains a top choice for roads, airport runways, parking lots, and even athletic tracks. Its ability to be recycled and reused makes it both economical and sustainable. Every new road starts in the lab, where engineers test, tweak, and perfect the mix, because when it comes to asphalt, getting the details right is what keeps our world moving smoothly.